start, everybody. So we are starting a whole new section of the course, which is going to be linear shift-invariant systems and Fourier analysis. This is extremely useful math, like ridiculously useful. For those of you who are in perception, you've already heard about this. For those of you who are in fMRI lab, you already heard about Fourier analysis, analyzing signals with something. But any time you are involved in doing anything like signal analysis, where a signal can be a sound, output of an amplifier coming from a neuron, an image, a sequence of images, a 4D sequence of images, otherwise known as what comes out of an MRI machine. Anytime you deal with data like that, this is ridiculously useful math. And it extends beyond what we've done so far by adding only one property. Because we already know what a linear system is, so now all we're going to do is specialize to a subset of those systems which are shift-invariant. There we go. So linearity, we know what that is. We've done nothing but linearity for the last month. Okay, so linearity is a system takes a signal in and another signal out, and it's linear if you scale the input signal, you scale the output signal by the same amount, and if you sum two input signals, you get in the output the sum of what each one of them would have produced alone. So that's the homogeneity and superposition, the scaling properties. So now we're going to add a new property that's fairly simple. It says that this system doesn't know what time it is. So let me unpack that remark. Systems, we've never said what the wires were generally. They were just numbers that came in and other numbers that came out. But if that sequence of numbers that are coming in is literally a sequence in time, and I will often use time as the axis of the various numbers we're putting into a system. So if those numbers that go into the system are the input at time 0, the input at time 1, the input at time 2, the input at time 3, what I'm saying is the system doesn't know what time it is. Meaning, if you kick it at time 0 and get some long-winded output, if you kick it at time 1, you get the same long-winded output except shifted one moment of time later. That's all I mean by shift-invariant. So you give it an input of any kind across its various input wires, and you get an output. If I take that input and start it somewhere else, some time else, then you get the same thing you would have gotten except shifted to that time. So I'll show you the image of those. But first, let's just point out that these are two different properties, and that they are, in some sense, independent properties. You can have a linear system that is not shift-invariant. You can have you can have a shift-invariant system that's not linear. So, as an example, so here's our little times and our output. So if I put in this and get out, boop, 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 and if I instead put in this and get, okay, linear system is just for each impulse we have to say what the output's going to be, and then we can do sums. So for this impulse I'm getting that, for this impulse I'm getting that. That's perfectly fine for a linear system. But it's clearly not shift-invariant because this guy shifted a little bit later, but this guy shifted later doesn't look anything like this. So this description of a system is something that could be linear, but definitely is not shift-invariant. On the other hand, here's a very simple system that's shift-invariant but not linear. Okay? It takes whatever number you give it and it spits it out immediately squared. Okay? So if I kick it with a 2 at time 0, I get a 4 at time 0 and a bunch of zeros. If I kick it with a 2 at time 10, I get a 4 at time 10 and a bunch of zeros. So I shifted the input, I shifted the output. But it's clearly not linear because if I put in a 1, I get, at whatever time, I get out a 1. If I put in another 1, I get out a 1. But if I put in 1 plus 1, I get out a 2, which is not, I get out a 4, which is not equal to 1 plus 1. Right? Not linear, meaning it does not obey superposition. So these are two different properties, but when you get them both, all of a sudden life incredibly simplifies in terms of what the system terms of how to analyze the system, in terms of what you have to measure in order to know what the system does. So here's the idea. Suppose I have, so you've seen this kind of diagram before, and L means it's linear. So you've seen this diagram before. It says, if I have this input, and I know what this guy would have done alone, this is a 1. And if I know what this guy would have done alone, this guy would have done alone, I can predict what it does with any of these by basically taking a weighted sum of those. That's the matrix multiply of like the first day in class. All right? In a linear system is a matrix multiply. However, shift-invariant means that if this 1 in position 0, and I'm counting from 0 instead of 1 today, and all my slides will count from 0, not count from 1. So if you do it in MATLAB, MATLAB's going to want to count from 1, and so you'll have to be careful about it. But in any case, if I put in a 1 at time 0, I get some output. Shift invariance means if I shift the input by 1 time step, I shift the output by 1 time step, but nothing else changes. Okay? This is shift invariance shown to you. And here I'm just showing you the shift invariance just for impulses, but linearity will buy you shift invariance for everything else. The shift invariance just means if you take the input and shift it some position in your vector, then you will get the same output you would have gotten shifted the same number of positions in your vector. Okay? And so remember that this sequence of things, that's the matrix that summarizes the linear system. It's just these guys. This is the first column, the second column, the third column, the fourth column. This is the matrix that describes a linear system. But now we're shift invariant, which means, well, look at that. All the rows are the same except shifted, which means I only have to measure it once. And then I know what all the other rows are. So now we've simplified determining how a linear system behaves to any input by not just measuring it for all of these, but just measuring it for one of them. Okay? So that's the huge simplification that this thing now brings you. Now there are some issues because the math we're dealing with is for, finite discrete math, meaning a vector is not infinitely long. It's the kind of thing you can actually have in MATLAB. A vector is a finite length thing, which means as I keep shifting these, eventually something's going to fall off the end, right? And that's a problem. So we have to figure out what to do with the boundaries. And there are all sorts of different conventions or possibilities for dealing with boundary effects. They're a bit of a nuisance, and the standard one that the math gives you is a bizarre one that we'll talk about later on. But you could just say, well, anything that falls off the end, we just ignore, because we don't know the input then, so it's 0. We're not going to look at the output then. We could extend our input and make a bigger input, so we have the input we actually want to analyze, but we could extend it on both sides with a bunch of zeros, long enough that the impulse response, which is what this is, doesn't fall off the end anymore. So you could avoid the boundary effect by just acting like you have a bigger input. So there are various things around that. But other than that, mathematical nicety, the math goes forward. And again, it's a linear system, which means that once you scale the impulse response shifted the right amount by the amount of the input at that same time, once you make this one, make the third one upside down and smaller, and you make the fourth one right side up and a little smaller, and you make the second one a little bit bigger, and the first one smaller. Once you do these scale factors from the input, you add them up, you get the output. That's the linearity part. The shift invariance part is the fact that these impulse responses are all the same, shifted. Okay? And so this, if you measure it, is the only thing you need to measure. If you know that it's linear and you know that it's shift invariant, then measuring this one time only, you don't know everything. And you can predict the result from any input whatsoever. So it's even simpler than a linear system, because rather than having to measure 4 different impulse responses, you only have to measure 1, because shift invariance gets you the others. Okay, so this, yeah?
Does the amount of shift in the output have to be the same as the
Yes. Shift invariance, the definition is shift. So if you think of this as the time axis, which I'm often going to, it doesn't have to be time, but I'm going to use that as a simple example because we're going to spend most of our time talking about one-dimensional signals, maybe written like a vector. And so yeah, what I'm saying is, if I move over by 1 second, or whatever this time axis is, then the output moves over by the same amount of time. So yeah, it has to be the same.
I don't quite understand what this is getting us, because if you have a linear system that has a one-dimensional input and output, don't you also only have to measure one input to know if that's varying?
Absolutely not, because the examples that we've spent the last month doing, you have to measure this one, and you have to measure this one, and it could be different. And you have to measure this one, and it could be different. And you have to measure this one, and it could be different.
But then you have a multi-dimensional input.
Nope. Well, we always have a multi-dimensional input. This is the way I've drawn it, we have a four-dimensional input.
Yeah, so four-dimensional input, you have to measure
Okay.
four connects.
Here's what's tripping, maybe what's tripping you up, but what I could imagine could confuse the whole room. I've used the word dimension two different ways in the last two sentences. Okay? Our input here has four numbers. It is a four vector. We would call that, this vector lives in 4D space. But, though that 4D space is the output at time 0, the output at time 1, the output at time 2, the output at time 3. So thought about as a function of time. It is a function of one dimension, time. It's not a function of x and y and t, like a movie. So think of a movie. It's put on your computer screen at low res. It's 512 by 512 by 60 images per second, say. So 1 second is 512 by 512 by 60. So we normally colloquially refer to that as a three-dimensional signal because it's got x, y, and t. But in linear algebra sense, the number of dimensions is 512 times 512 times 60, because that's the number of numbers in the vector. Okay? So I think that may be underneath what you asked, and I'm glad, because it's very easy to trip over that. When I call this a one-dimensional signal, it's not one-dimensional in the sense of the last month. It's one-dimensional in that there's a time dimension, but there's no space dimension. But of that time dimension, you're getting measurements at very many different times. So your vector has a bunch of numbers in it. So in vector space terms, your vector is, well, right now 1, 2, 3, 4, 5, 6, 7, 8 dimensional. Okay, so I'm using the word dimension two different ways. Sorry about that. It's appropriate to use it in those two different ways, but I will try to be clear which one of those ways I mean at any given point in time. Okay, so first of all, let's think about what we got here. I'm going to have a slide that looks like this later, but I actually want it on the board right now, because to accompany the next slide I'm about to put on the board. So it's a linear system, which means it's a matrix multiply. And we have the matrix sitting over there, and as usual, you know, these impulse responses become columns of the vector. So what have I got? I've got the impulse responses right here. Small, big, smaller, smaller, smaller. So the vector, the matrix that is our linear system, L equals, the first column is small, big, smaller, smaller, smaller. And the second column is shifted, small, big, smaller, smaller, smaller. And the next column is small, big, smaller, 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 dot, dot, dot. Everything else. Okay? That's the usual thing. Because the columns give you the response to the system seen from the input perspective. So if I put an input here, you know, for example, this guy, which is this, little negative, this guy contributes to the output, this column scaled by this number. So this is the impulse response that you get for something at this time. This next column is the impulse response you get for somebody a moment later. And shift invariance is these columns keep shifting down. They're all copies of each other, shifted by one each time. Okay? So this is a matrix corresponding to what we're looking at here. So that's the input perspective, right? Remember when we talk about matrix multiplications, there were two different ways to talk about it. One of them was, for each piece of the input, how much does it contribute to the output? It contributes a scaled copy of its corresponding column. Then we have the output perspective, which is looking at the rows. So the output perspective is an operation called convolution. So let's take our input and our output, write them here. This is a different input than the previous slide, but whatever, it's a sequence of numbers, and here's a sequence of numbers coming in the output. And each output is going to be a weighted combination of inputs. Now, if I think of the x-axis as time, you'll notice that I've only included some of the input in the output at time 3. Why did I do that? What property has to be true physically for any system whatsoever that is obeyed because I drew it the way I did? The output can only depend on what part of the input. My output right now can only depend on what happened in the future, past, otherwise known as systems have to be causal. Okay? And if we're going to think of the x-axis as, I mean, in non, if the x-axis isn't time, this isn't important. But if we're going to treat the x-axis as time, my output now can depend on the input now and the input in the past, but can't depend on the input in the future. So this particular slide is written specifically to be causal. If the x-axis is something else, if it's space, that doesn't have to be true. But for time, if you're going to write a linear shift-invariant system, its impulse response, when you kick it, the output can only happen in the future. It can't create outputs in the past when you kick it now. If you figure out how to build such a thing, please tell me. We can all get rich together. Okay, so the idea is my output now depends on the input now and the impulse response that's instantaneous. This number. I also get some contribution to my output now based on something that had one time step ago. That guy's going to create an impulse response, but in order for it to contribute to this time, a time step later, it's not the beginning of the impulse response, it's one further along in the impulse response. It's this weight. So this is getting the first piece of the impulse response. This is getting the second piece of the impulse response. For somebody 2 time steps ago to affect me now, it's got to be his impulse response after 2 time steps have occurred, otherwise known as this guy. So if you see what I'm spelling out here, the weights from the output perspective, what my output is now depends on the input now based on the beginning of the impulse response, the input a little while ago based on a little while ago in the impulse response, etc. In other words, these weights here are the impulse response flipped. Now, how do you see that in the matrix? We're doing the row version. Oh, I should have done, whatever. Yeah, so I have to do a little bit more. I'm going to do one more. So here's one more row in the matrix, just so I can show you a little bit more of it. And we're doing the row version, right? Because we're doing the version from the output perspective. And look at the impulse response. Small, big. Oh, I have to do one more because of the one I circled. Okay, actually that was the right one to do. Okay, except that I wandered off into the wrong row. Okay, so look at this set of weights. Those are the little R's over there. And look at it, small, bigger, 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 small. As opposed to small, bigger, small, small, small. It's backwards. It's flipped. This has always been true for these matrices. For a shift-invariant matrix, that's what you get. So just written out, the output now is the sum over inputs times the impulse response flipped. This is k, this is minus k. Okay? N minus k plus k is n. So the output at n is the impulse response at 0 times the input now plus the impulse response at 1, k. And 1 time in a moment ago times 1 moment forward in the impulse response, and so on. This and this are identical. One way is flip the impulse response and do a dot product with the input. This looks an awfully like a dot product, doesn't it? And the other way is flip the input and dot product with the impulse response. Whether you do it this way or this way, the dot product doesn't care. Okay? So this is the output perspective. it's a bunch of fanciness that basically says, I want to take these rows and dot product them with the input. The only other fancy thing is, if the x-axis is time, what k's do we sum over? And the answer is, in this perspective, where we're asking for the output at time n, we're going to sum k from 0 to n. We're not going to go to n plus 1, because the output at time n can't depend on x at time n plus 1, because that wouldn't be causal. If the x-axis is something other than time, that's not an issue. And so this is always the formula. This is just a way of writing out the dot product of this matrix, where R, the function R, is this. This is R. And the rows are R flipped around and shifted. And the flipped around and shifted is the n minus k. Okay? So this is just putting in symbols when I already said what you already know about the way matrices multiply.
Are you saying this only works if the dimension is time?
No, the only thing that's special about time is the causal thing. But all the equations otherwise, and the shape of this matrix and everything else, is fine even if it's not time. The only thing is, if it's not time, I don't have to be causal, which is to say the impulse response can depend on positions. Let's say this axis is space, x. So this is, when you kick me here, I produce outputs to the right of me. I can also produce outputs to the left of me. Who cares? That's fine. Now, thought about this way, this is a dot product with your input. So another way to think about this, and let's actually go with Julian's example, let's go to space for the moment. And so one thing we're saying is that the row perspective is the output perspective. It's saying that when we produce our output, y, that the output here is a dot product of this with one of these rows, and it's saying that my output depends on the corresponding part of the input and some of the neighbors with these weights. So suppose those weights were, let's do this. Here's the axis. Suppose those weights were this. I'm going to make it be an impulse response at 7 things. 1, 2, 3, 4, 5, 6, 7. Okay, suppose that's it, and this is the position that corresponds to the input. Okay, so we're going to do a dot product with the input that looks like this. Dot product with the input centered on me, and for different outputs, all centered on where that output is. So I'm going to shift this thing around. Does this picture look like something that anybody here, having taken intro neuroscience or intro psychology, has ever seen before? I'll make it look like a function continuous, even though we're doing discrete math. Seen that before? It's a receptive field. And it's a standard receptive field in audition, in vision, in somatic sensory, and everything. Surround inhibition. Okay? So the concept of a receptive field, I assume that's a comfortable concept for basically everyone in the room, is a neuron responds to whatever sensory continuum it's responding to. Could be touch, could be hearing, where the axis is frequency, could be visual receptive fields, where the axis is some aspect of space. That this neuron is excited by nearby inputs and inhibited by inputs to either side. Saying shift invariant is we're going to consider a system where there's a bunch of neurons that all have the same receptive field but centered on where they are. So you asked about why are we adding this extra constraint, what are we buying with it? We're buying a description of a kind of system that we run into all the time. Now it is true that the retina is not uniform. Ganglion cells do not behave the same way in different parts of the retina, but in a locale of retina it may be reasonably uniform, and we can turn our attention to one particular neural type in that piece of retina and say, what is the signal processing that neuron does if it's got a bunch of brothers and sisters that are the same as it, but just in neighboring spatial locations. Okay? So that this row vector is the impulse response flipped, one way to think about it, or it's that thing which you dot with the input, that it's the way you weight the input to produce an output, which is exactly what we mean when we draw pictures like this and say that's my receptor field. So as we go through this math, you can think about it as a receptor field. When we talk about time, it's still a receptor field, but it's a receptor field over time. It's saying my output now depends in this linear way on what's happened recently. But when we do it time, it can only be towards the past, not towards the future, so we'll have that causal requirement. When it's space, it's not causal, and it's often symmetric or anti-symmetric around here. Okay. So that's the output perspective. And so the idea of convolution, so what we're doing is an operation that combines the input x and the impulse response r. And this formula is called convolve x with r. I don't know if the notation's in the next slide, but we can say that y is x, usually a star, r, where star stands for not multiply, but stands for convolve. It's something that takes two functions, takes one of them, flips it with the other, and then dot products it at various locations. So what you'll see here in the animation as you look up, I think that's what happens now, is that that's showing you the output at time 3. That's showing you the output at time 4. That's showing you the output at time 5. Arrow doing a build, who knew? Okay? So convolution is take that dot product and slide it around. The slide along comes from what property of the system? Shift-invariance, not causal. R could have numbers that are going to the right if we're non-causal. But the fact that the output at the next time step is the same operation applied that time later, that's shift-invariance. There it goes again. I think this can end soon, please. Thank you. Okay, so one way to think about it is a sliding dot product, which is what I just showed you. Another way to think about it is that it's just a linear system, so it's just a thing with a matrix, except the matrix has structure. Whatever's in the first column is in the second column shifted down by 1, is in the third column shifted down by 1, is in the fourth column shifted down by 1. That shift is shift-invariance.
What did you put the bottom?
What's that?
Is it zeros on top of it?
Well, if the impulse response only lasts a finite amount of time, or space, or whatever it is, so the way I've drawn it is the impulse response is 5 thingies, so everywhere I haven't drawn a thingy is 0. If you had an infinite impulse response, suppose it was time, and when you kick it, you get a response that lasts forever, and I will talk about such a system in a slide or two, then this is going to keep going. When you shift it down, a bunch of stuff's going to fall off the bottom, because we're dealing with finite matrices, but we're dealing with a system that goes on forever. There are analogies, and there's a slide about this that we won't get to till next week sometime. There are analogous bits of math that don't do it for discrete and finite amount of time. You can do the same math for an infinitely long vector, but you can't write a matrix. And you can do it for continuous time. There are versions of it like that that are perfectly analogous. The intuitions I give you all work for all those other versions. But, if you're going to run it in MATLAB, it's got to be a matrix that, runs out, only uses a finite amount of memory. So that's why we do this version. But yeah, it just slides down, 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 down. And if I act like the impulse response is of finite length, then where I don't write it, that's the numbers are 0. Yeah?
For the R's, you have R0, R2. As you slide down, do you have an R3, R4 as well?
If you have an impulse response that lasts more than 3 time steps, then there will be more of them. Like the one over there should have an R3 and an R4. Because there are five numbers.
So if your dimension is in time, you can only cut it with 0 cutting, right?
If your dimension is time, there can't be an R-1. Because an R-1, the way I've drawn it, would be something that the input now depends on one time step in the future. Right? If I had an R-1, it'd be pointing this way, meaning my output now would depend on one time step in the future. So if it's time and you want it to be causal, the R's only go back in time.
So the boundaries has to be 0 cutting.
Boundaries is a separate issue. And I want to dance around the boundary problem for a while now. I'll have a slide where I talk about it, and at some point I'll talk about what actually happens in MATLAB, which is a particular boundary treatment that will seem bizarre to you, but there's a reason for it. Well, I'm not ready to talk about boundaries yet. Just say boundaries are an issue. We'll return to them. Sorry to around that, but it'll just be easier didactically to do that. So you'll notice that the numbers are going backwards because it's convolution. When we did it as an impulse response, if I wanted to label these little dots here, this is R0, this is R1, this is R2, this is R3, this is R4, right? So the numbers are going up here because if you kick it at time 0, this is the output at time 0, the output 1 time step later, the output 2 time steps later. This is causality. When you kick it, you only get results in the future. You can't kick it and have that affect the past. Okay? And thought about in the output perspective, you flip it around, and it says that my output now depends on the input now and the input in the past, but doesn't depend on the future. So either way of thinking about causality, when you kick it, it can only have effects in the future, or when you look at the output now, it can only depend on inputs from the past. Those are both saying causal. And the fact that one time I was talking about the future, that's the output perspective, and the next time I was talking about the past, sorry, did I say that backwards? When I was talking about the future, that was the input perspective. When you kick it, what happens? And when I talk about it this way, that's the output perspective, and it says my output now only depends on now in the past. All right, so here's a picture of what I drew on the left. And so again, this is the impulse response. A column is the impulse response. If you kick it at time 0, here's what you get. And the fact that it's shifted down is exactly what I drew before. This is one example of dealing with the boundary problem, which is it just falls off. And that's something one can do. The rows is, as you can see here, just as I've been describing, is the impulse response backwards. So negative, bigger, negative, 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 bigger, negative, negative. Now I'm going backwards in the thing here. I'm going forwards. It just comes from when you slide it this way. The rows end up being the same as the columns backwards. So what to do about the boundaries? Yeah. So there are lots of things one can do about the boundaries. If you're dealing with images, well, okay. I'm going to come back to some of the ways to deal with boundaries later. As a hack or a reasonable thing to do, and in software, for example, Arrow has a huge pile of software he produced many years ago that's used in his lab quite a lot, and a lot of people use as well for dealing with filtered images, filtered in different ways. And it has built in some standards that one can call about how to deal with the boundaries. MATLAB itself also, if you call the convolution function, has some parameters for what do you want me to do when I fall off the edge? Do you want me to deal with that as being 0? Do you want me to... So you've got your impulse response, which is sliding across your input. The problem is when the impulse response is trying to access parts of your input that you haven't supplied. Okay? So if you want to find out the output now, but your impulse response wants to refer to inputs that you didn't give them, the question is, what do you want to consider those to be? And I forget what all the ones are in MATLAB, but things that people often do for what do I do with the input, here's the input, so let's call this, x1 to xn, okay, that's the input. So the question is, if I want to have an impulse response hit xn plus 1, what do I consider it to be? I can consider it to be 0. So I can just put 0, embed my vector in zeros. That's one standard thing to do. I can extend it out the edges of the way the input was. So I can put xn here, and xn here, and xn here. Put x1 here and x1 here. So I can just extend with the edges of the input so it doesn't all of a sudden change. Because when suppose this is a big number, that your input ends with a big number. If I extend with zeros, that means I'm putting a huge change right here, which will be noticed when you do your convolution. It'll have a huge effect to have a big edge there. If you don't want to have an edge, you want to act like, well, I don't think it changes much, then you can just make it not change at all. Another thing you can do is make the derivative not change. So if this is xn minus 1, you could have this be, well, let me do it in pictures rather than in numbers. If this is xn minus 1, xn plus 1, this is this, and this is this, I could say, oh, let's just extrapolate. Make this be this. Okay? So that would make it so that the derivative doesn't change there, the slope doesn't change. That's another thing you can do. The thing you actually do in the math, which I'll explain much more probably next time, maybe we'll get to it today, is you act like your input is circular, which is to say after you go to xn, you go to x1 again, x2, x3. That seems bizarre, because if this is time, you're saying that after I've done my whole sequence, somehow I go back in time to where I was. So that's a weird thing. I'll explain the circularity nation a bit later and why we do it.
What does the nervous system do with this problem? Like, for instance,
Well, we live in continuous time. We don't have this problem, right? If you talk about the time axis, we're just living it. And if some aspect of your sensory apparatus is effectively summing what's happened in the recent past, it just does that and keeps doing it.
but in terms of space. So, for instance, how we see.
Yeah, so first of all, shift-invariant means we're doing the same thing over in this part of the retina as this part of the retina. We don't. In little aspects of the retina we do, but as you get more towards the periphery, things do change. So your visual system is not shift-invariant. And not in this class, but in other classes, perception, likely you'll talk about that. But nevertheless, in a local region, it may act shift-invariant. Just like systems are never linear. They can't be. If you multiply the input by 10 to the 16th, you just fry the eye. You can't act like you're linear. But in a range, it may act linear, so the math may be useful in the range of things you usually encounter. So you can still use the math even though you acknowledge its shortcomings. Okay, so let's move on. We'll get back to this boundary thing a little bit later. Now, everything I've been talking about, the impulse response has been finite. It's been, 3 times steps worth of output when you kick it, or 5 or 7. Those are called finite impulse response systems. But there are also things that are called, so that's what this stands for, finite impulse response. But sometimes you get a system where you kick it and it'll last forever. And one way to build such thing, which is a standard thing that you would get in engineering school, way back when, are systems where they do this linear thing. So here's the input, here's the output. And what I'm going to do is going to be a linear combination, a weighted sum. But not just a weighted sum of past and current inputs, but also a weighted sum of past outputs. Okay? That's an extension. We're not putting this in a matrix anymore where all that comes in is x. Because now, here's a dot product, but part of the dots are with x. And so part of the dots are with past y's. Okay? So that's, I'm just going to talk about that for just a brief moment, just because it's a standard thing and a useful thing, and you may even run into it at some point. And so I'm going to give you the simplest of all possible examples. So suppose I have such an input where I say that the output at time n is going to be a weighted sum, as written there, of various inputs and various outputs. And I'm going to make it really simple. I'm going to actually use real numbers too. I'm going to take 0.8 times what the output was the previous time step, plus 0.2 times the input now. Those numbers are 0.8 and 0.2. So what is the arithmetic thing I'm doing called? I'm taking 80% of this and 20% of that. So what I'm doing with those two numbers in English. You're saying it. Say it. I'm taking a weighted average, right? I'm taking a weighted average where I'm giving a high weight to what my output used to be and a low weight to the new input. Okay? So let's figure out what happens. Suppose my output at time 0 is 0. I'm going to give it an initialization. Okay? And so at time 1, y1, so I'm going to say y0 is 0 by fiat. Let's just assume that's true. So y1 is going to be 0.8 times 0. That'll go away. So it's going to be 0.2 times x1. Right? So now let's go to the next time step. y2 is going to be 0.8 y1 plus 0.2 x2, which is, now I can substitute what y1 is. It's going to be 0.8 times 0.2 times x1 plus 0.2 times x2. So another time step. y3 is going to be 0.8 times y2 plus 0.2 times x2, which is going to be 0.8 by the time I carry this out a whole bunch of times, the output is going to be, everything gets a 0.2 on it. What did I just do? I left out the other guy. 0.2 times x3. Is there another mistake someone caught? No. Okay. So there's a whole lot of 0.2s in here. Everything's getting a 0.2 always. So yn is going to be 0.2 plus 0.8 to the nth. Let's see, x. It's going to be n minus 1. 0.8 to the n minus 1 x1 plus 0.8 to the n minus 2 x2 plus dot 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 up to the current thing. Otherwise known as the impulse response, is going to look like this. .8 to the nth power, otherwise known as an exponential. Okay? So it's an infinite impulse response. It goes out forever. It never gets to 0. And it happened that way because you're always retaining part of the previous output and scaling it by numbers that are non-zero, so it never goes away. It is an extremely standard linear infinite impulse response system. It shows up everywhere. If you were, an undergraduate engineer, it's the first circuit you ever learned about. If you have some voltage sitting here between this place and ground, and you put it through a resistor and a capacitor, which is just two parallel pieces of metal not touching each other, and you measure the voltage. So this is voltage in, and this is voltage out. That system, called an RC circuit, is an exponential impulse response, where the time constant, meaning how quickly it drops, is resistance times capacitance. Now, why am I giving you the circuit? Well, you don't care about electronic circuits here. We're neuroscientists and cognitive scientists, okay? Think axon, dendrite, any cable, anything that's got electrical stuff going on in it that has a resistance to current going this way and a capacitance to somewhere else, and a cable is something that's got an insulator at the outside of the axon of the dendrite. You put a voltage at one end of the thing and watch it flow down the cable, the basic cable equation, until you add some fancy ion channels doing interesting things. Before you get to that, a passive cable, like a myelinated axon before you get to the next node, any such cable behaves exactly like that system on the board, with weights that look kind of like this. So exponential impulse response is like the dumbest, simplest, most expected temporal impulse response you would ever get from any interesting system. Finite ones in time are rare. Exponential ones are extremely frequent. In cognitive science, they're used as models of memory everywhere. They're kind of a standard thing. So infinite impulse response is not a trick or a mathematical nicety. It's actually a very useful thing. However, in this class, we're doing discrete math, and so we're not going to return to them. But just a pointer to the future, they are useful objects. The math you need, varies a little bit, because just doing it as a matrix is silly, because everything's going to run off the bottom of the matrix all the time, because every impulse response is infinite. Okay, so we're going to stick with finite ones from now on. But another thing we're not going to do in this class, and for those of you in MRI lab or perception will have seen this, I talked about dimensionality two different ways a while ago. So our vectors, as long as they have more than one number in them, are multidimensional. But there's another version of dimension, which is how are we thinking about our input? If it's time is a dimension. We may sample it lots of places and have a multidimensional vector. But time is one-dimensional. But sometimes we want to use shift-invariant math for things that are more than one-dimensional. For example, space. So I drew a receptive field as a little center surround thing like this before. But normally, if you're thinking of vision is not just x, it's x and y, which means we spin that guy around and we get a receptive field which is excitatory in the center and inhibitory in the surround, where the dimensions are x and y, and the little numbers in there are pixels. So as a vector, it's lots and lots of pixels again, that 512 squared idea. But as interpreted as a function of space, it's two-dimensional, meaning the x dimension and the y dimension. And shift invariance means, I have my receptive field, a bunch of numbers. Maybe a +8 surrounded by a bunch of -1s to represent that guy, right? Here's the +8, and then I've got 8 - 1s, a really simple receptive field. But I want that guy to apply the input everywhere, which means it can shift to the right, and it can shift down. So if you keep the input as a matrix, and if you think of convolution as taking this other submatrix and sliding it around and doing dot products, but preserving the two-dimensional geometry of the input, that's what we mean by 2D convolution. Now, the input is just a bunch of numbers. The input being as a bunch of numbers that have an x and y, we would think of as a matrix. But for the shift-invariant math stuff, we've been talking about vectors, which means we take all those pixels and line them up and make one hugely long vector out of them. But in order for convolution to have this, what I mean by shift to the right, what I mean by shift down, we really have to think about it a different way. We have to think about the pixels as not 512 squared big long one single vector, but rather 512 and then another 512 over here and then another 512 over here. So that geometry needs to be preserved when we think about that version of 2 dimensions, x and y. Okay? So I keep using the word dimensionality 2 different ways, and it's important to keep the distinction available to you. So convolution again is take the impulse response and flip it around, and then do dot products everywhere. Okay, but the dot product now is put that 3 by 3 on top of the 3 by 3 pixels, multiply and add. Okay, so we're not going to do the 2D version here, and you can do it in 3, and you can do it in 4, and anytime you're analyzing fMRI data, you're doing it in 4, right? You've got x, y, z, because it's a 3-dimensional image, and you've got time, we've got multiple scans, and so you can talk about filtering your data with a kernel, a impulse response, flipped around, a kernel it's called sometimes, that has x and y and maybe z and maybe time. Okay, so it's the same ideas, but paying attention to the fact that my data is not just a vector. Those numbers have some structure to them, because some pixels are below me, some are to the right of me, some are further dorsal in the brain, some are from one time step later. So it's still a lot of numbers, which you can think of as a vector, but you also really want to pay attention to geometry. So when you get to linear shift-invariant systems for more than this kind of dimension, you want to preserve the geometry when you think about what convolution does. It's the only time we're going to touch it in this class. In perception, obviously, you'll see more of this. Okay. So that's a linear shift-invariant system. It's just a matrix that has that structure on it. Where are we at? I'm going to take an early break because this is a choice point. So I'm going to take a break right now. Come back in 3, please, so we can get somewhere with the rest of it. What we've done so far is to say if a system is linear and shift-invariant, you can measure its impulse response, and that's what you get. And if you want to describe it from the output perspective, it looks like the operation that we call convolution, which is take the impulse response, flip it, and do a bunch of dot products, sliding along. Okay, so where we're headed is the usual way to talk about linear shift-invariant systems, which is in terms of sine waves and frequencies. So for the next day and a half of this class, we're going to get some heavy reminders of trig that you may have forgotten, that I certainly have forgotten, and always have to rederive or look up on Google. So as to what happens when you do cosine. So first of all, we're going to talk about what we mean by discrete sine waves, discrete cosine waves, because we're doing this all as discrete math. So, here's a cosine. N is which entry in our vector, right? Think of that as time step, if you will. And it has a frequency called omega, written as cosine omega n. Omega is in units, so we're assuming that cosine is the usual cosine function where the argument is not in degrees, but is in radians, where 2 pi is like 360 degrees. So omega is in radians per sample, meaning you increase by omega radians when you go from n to n plus 1. So omega is these funny units that we're not all necessarily comfortable with. So we usually state omega in these terms. So if the length of our vector is capital N, we're going to have omega be 2 pi k over capital N. So k now is in units that are much more sensible. It's in how many cycles of this cosine wave per the length of my vector. How do we know that? Suppose k was 1. So now omega, as you go from 0 to n minus 1 across your vector, cosine of 0, cosine of 2 pi over n, cosine of, what am I trying to say here? Yeah, so suppose k is 1. So we're going to multiply by n, so it'll be omega times n, and omega is 2 pi over n, so we'll be taking cosine of 2 pi over n, 2 pi over n times 2, 2 pi over n times 3, 2 pi over n times 4. By the time we get all the way to the end of the vector, we'll be at 2 pi times n minus 1 over n. And if we had one more point on our vector, if we could get to the next place, we'd be back where we started. So when k equals 1, we get one full cycle. We get one amount of 2 pi as we go across the vector. When k is 2, we get through that cycle twice. When k is 3, we get through that cycle 3 times. So k is now in reasonable units. It's in cycles per vector length. So here is an example with k equals 2. It's cosine, and I'm going to name my time steps not with the MATLAB convention, but I'm going to start numbering from 0. So if I've got 32 elements of my vector, the indices are going to go from 0 to 31. And so when k equals 2, by the time we get halfway to 16, and n is 32, k is 2, so k times n equals 16 is 32 over 32, so we've already gotten to 2 pi by the time we get to 16. Meaning we've gone through one whole cosine wave. Up to down, back up. That's one cycle. And if we got to number 32, we'd be there again. But we don't quite get there because we end at 31. So we don't get quite back to the top. We're one short of the top. Why is that? Well, I'll keep alluding to this because now I've let the cat out of the bag. Here's a vector that represents 2 cycles of a cosine, except we haven't quite gotten back where we started. But imagine if I took this vector and put it over here as well. Then they would concatenate very nicely because I go from here to the top of the cosine and continue on down and up and down. Okay? So the math often treats the boundary condition as if we go right back to the beginning. As if it's not a vector like this, but it's in a ring. And I said I wouldn't do the 2D version like space, but in the 2D version like space, if you did, if you do a 2D Fourier transform, whatever, use the math that we're heading towards, it treats the left edge as glued to the right edge, and the top edge is glued to the bottom edge. Otherwise, it takes your flat image and treats it like a donut. Okay? So that's the boundary conditions that the math typically uses and that MATLAB typically uses for the stuff we're headed towards. And it has this nice property that if I put this over here, it nicely concatenates.
Just remind me what the x-axis is.
Well, the x-axis is just, I'm going to have some vector that I'm going to put through a linear shift-invariant system, and I'm going to, for now, have the input vector be a cosine. And I'm just giving you, here's what I mean by cosine. But the x-axis is also, well, let's imagine that my vector is not just 32 numbers, but it's 32 numbers sampled in time at equal intervals. Okay? All right, so that's your basic cosine. Now, you can be more general than this. So our basic cosine has a frequency, k, that's an integer. We're not going to talk about 2.5 cycles per sample because then the concatenation will fall apart. But for k an integer, it'll nicely work that if I take my signal and then repeat it, it'll repeat in exactly the way you'd want it to, which is to say it'll just continue along in time. So the k's are going to be integers, just like the positions in my vector are integers, position 0, position 1, position 2. The k's will remain integers. But I might want my sine wave to move around. And if I want to allow my sine wave to move around, change amplitude, change position, the most general sine wave is written this way. A is just a scalar multiply, so it stretches or shrinks it if A is a positive number, possibly flips it upside down if it's a negative number. Minus phi says my value now is what the cosine would have been phi radians ago. So, in other words, if phi is a positive number, it means take this wave and shift it to the right. So phi is a shift. Why do you think I'm interested in shifts? We're talking about shift-invariant systems. So shifts are obviously relevant, and this is a shift in radians terms, so it's called a phase shift because it's the phase of the wave that we're going to shift by. Okay, so this is your standard notation for it, so what does it do? So suppose I have a AB 1.5. It means that the peak is no longer 1, the peak is 1.5. Suppose that phi is 8 pi over 32. So that's in radians. It's a quarter of pi. Pi is 180 degrees, so I'm shifting by 45 degrees. But another way to think about it is 2 pi used to be 32 samples, right? 2 pi is the whole signal. And I'm shifting by a quarter of pi, which is an eighth of 2 pi. 2 pi was 32, oh, wait, did I just do the arithmetic wrong? I did. Where did I screw up? Hold on a second. 1 quarter of pi is 1/8. Is the picture wrong, or is the... No. Maybe the picture's wrong. When I looked at it last night, I thought the picture was right. But you look at the picture, this picture has been delayed in time. And it's been delayed in time by 2 samples. Here's the extra 2 samples, because this sample used to be at time 0. It's been shifted over 2 samples. Oh, I'm sorry. Sorry, this is in here. Yeah, it's in the cosine wave. I neglected the frequency. It's 45 degrees in the sine wave, not in the vector. Sorry, the sine wave's half there. So 16, where an eighth of that is 2. We shifted by 2 samples. That was my mistake. Okay, let me say that all again, because I'm sure I confused some of you. Here's a cosine. Omega is still this omega, right? K is still 2, right? There's 2 cycles here, there's 2 cycles here. I'm going to phase shift it for my cosine wave this many radians, which is 45 degrees, which is 1/8 of a cycle. A cycle of this wave is 16 elements of my vector, so an eighth of that is 2 elements. So I've shifted this guy 2 elements to the right, meaning the peak one that was at 1, which is now at 1.5, is the entry 2 instead of entry 0, and these guys get filled in with more of the cosine wave. Okay? So this is just, I'm defining my terms because we're going to be using cosines a whole lot in the next hour and then the next 3 hours, probably in the next 5 hours of this class. Okay? So general cosine wave has general amplitude and general starting point. That's all. That's all I've added. It's got a frequency, which is omega, which we usually state in this terms, which means it's got an integral frequency per the length of your vector. And then it can be shifted, because we're going to do shift-invariants, we need to know how to do shifts, so here's how you do a shift. Okay.
If you want to shift like the other way,
You could have phi be negative. Phi positive means my output now is what a cosine wave would have been that long in the past. So you look in the past and put it now, which is shifting to the right. And so if you want to shift to the left, then phi will be negative. And the fact that we put a minus sign here is just a convention. It's a reasonable convention, because now phi, a positive number, means phase delay. Means shift to the right. Okay, but now let's go back to high school trig. Here's my standard formula for any old shifted sine wave. Back in trig, you learned a million identities, 2 or 3 of which we're going to use today. One of those identities, if you don't remember how to derive them and you're curious, you can help with that, you can look it up. But one of those identities was cosine of something minus something else, which turned out to be cosine of the 2 multiplied plus sine of the 2 multiplied. Okay? I'm sure you've all seen this once, and I'm sure you've all forgotten all those identities. I certainly have. But that's just one of them, and so I'm going to use it. Because this is cosine of something minus something else, which means I can apply the identity. The A is just a scale factor, so that'll just stay on the outside all the way. And then I'm going to say cosine times cosine plus sine times sine. Cosine times cosine plus sine times sine. Okay? But notice what we got here. This is a cosine wave of an arbitrary phase, phi. Phi could be anything. It doesn't even have to be an integer division of 2 pi radians. It can be any amount of radians. So I can shift by any amount whatsoever, but I can build that shift just with cosine and sine, with constants as weights. I can take a weighted sum of cosine and sine and get every cosine wave of every amplitude and every phase shift just out of these two. Now, I'm talking about cosine and sine waves, but they're also vectors, right? And we're in vectors the length of however long your signal is. And remember, that lives in a vector space, which has coordinate axes, which are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, and then a whole bunch of those other vectors. So there's a standard coordinate system of unit vectors that describes these big long vectors that we're now dealing with. A cosine wave is just a bunch of numbers in a vector, which means it's a vector pointing in some direction in that space that we've been dealing with for the last month. And a sine wave is just a bunch of other numbers, just shift by 90 degrees, but it's just a bunch of numbers. It's a vector. It means it's pointing somewhere else. Okay? So here's two vectors in our space, cosine omega n, sine omega n. They're not length 1, but we could divide by the length and make them length 1 if we wanted. Okay? And what I've just said is that if I want any other cosine wave of any amplitude or any phase, I can build it as a weighted sum of these. So here's a vector, cosine and sine. If I take a weighted combination of these, constant times this plus constant times this, I get a new vector. Where does that vector live in the geometry that we've been dealing with all the last month? It lives in the plane formed by cosine and sine. So what we've just said is that all the cosine waves with that frequency, omega, all live in a plane. And that if I add two of them, I still stay in the plane. If I phase shift them, they stay in the plane. As long as I don't change frequency, that's a plane in the 32-dimensional space that we're currently using as our example. Well, that's kind of cool. And we're going to use that fact a whole lot going forward. All right. We have these weights. The weight on the cosine wave and the weight on the sine wave. So here are the weights. Let's just call them x, which is a cosine phi, and y is a sine phi. So we've got x times a cosine wave plus y times a sine wave. So I could call this x, or I could call this y. But if you're in Cartesian coordinates and you have a vector x, y, you could also convert to polar coordinates. And those polar coordinates, guess what? Are a and phi. So this trick of thinking about weights on cosine waves as a weighted sum, x, y, or as an amplitude and a phase, which is polar, we're going to use that trick a lot, going both forward and back. Okay? So the math is just, I already gave you the math, it's sitting right here. It's just some trig identity applied to a standard cosine wave. I haven't changed anything, but I'm saying that I'm going to take a weighted combination of cosine and sine in order to get this guy, but the weights are just the Cartesian coordinates for which these numbers are the polar coordinates. Okay? Polar coordinates, length of vector. And what's the length of the vector? If I take x and y and square them and sum them, and then take the square root, I square them and sum them, I get a squared times cosine squared plus sine squared. And cosine squared plus sine squared is 1. And then take the square root and I get a. Okay, so I just did this math without drawing it on the board. But it uses the one trig identity I bet you all remember, which is cosine squared plus sine squared is 1. Okay? And this angle is just the arctangent of these guys. And so you can get phi from the weights. You can get the weights from phi. Okay? So those are two ways to think about when we shift a sine wave or scale it, how do we want to think about that? We're going to want to think about it relative to two standard sine waves, cosine, which starts at 1 and goes down and up and down and up, and sine, which starts at 0 and goes up and down and back and up and down and back. And so these two we're going to work with a lot, and then everything else we're going to derive as a weighted sum. Okay, so here's our shifted sinusoid again. That's saying stuff that I already said. So any scaled and shifted sinusoidal vector, so we're using discrete vectors, it's that we don't need the continuous math to do this. The discrete math works out not as an approximation but perfectly. But any scaled and shifted sinusoid is a weighted sum of only two sinusoids. Where we're headed over the next two sessions is we've got a linear shift-invariant system. We've summarized that what that system does by kicking it and seeing what comes out, and then that shifted in time will predict what it does to anything. Now we're going to take that same linear shift-invariant system and predict it by putting in things like this and see what they produce. And I'm going to show you in a moment that what they produce is really simple. And that's another important property that comes out of linearity and shift invariance. So we have these two fixed vectors. Here's the cosine one that I showed you before, for k equals 2, in fact, again. And here's the sine one, where we shift this over by 90 degrees. 90 degrees is, in this case, shifting it by 4 time steps. Okay, so I shifted this guy to the right by 4 time steps. What used to be the peak at position 0 is now the peak at position 4, and the rest gets filled in. Okay, so here's our cosine omega n, here's our sine omega n. They're just vectors, but given these two vectors, any scaled shifted cosine wave can be created as I weighted some of these two. Here's what the weights want to be from this a and phi. And you can either talk about those weights, or you can talk about it in polar, which is what you've got up here. Okay. What comes next? So as an example, a bunch of examples, I'll do this. So suppose the amplitude is 1.6 and phi is 0. 2 pi times 0 over 12, say. Okay, so phi is 0, so we're not going to phase shift the cosine at all. So I've drawn a vector whose length is 1.6 and whose angle is 0, so it's on the x-axis. Now we're going to talk about the coordinates of that vector. X is 1.6 and y is 0 for this vector, which means we're going to take 1.6 of this and none of that. Add it together and get cosine with amplitude 1.6. Now let's start phase shifting. Okay, so now we've phase shifted by, what is it supposed to be, 60 degrees, I think? I think that's what that is. Yeah. And so we get this vector, which gets some amount of cosine, some amount of sine. If you take this amount of cosine and this amount of sine and add them together, you get this wave, which still peaks at 1.6, but has been shifted over by, I think it's 60 degrees. If you shift over by more, oh, that must have been 30, this is 60, sorry. You shift over by more, still length 1.6, but now the angle is twice as big. So now the amount of cosine you need is less, the amount of sine you need is more, and there you go. You'll notice that this guy is just basically marching to the right by 30 degrees at a time. If we go by another 30 degrees, we now are at 90 degrees, which means this vector has all sine and no cosine. The x-coordinate is 0, so no cosine. The y-coordinate is 1.6, so we can take this guy and scale him by 1.6, and that's exactly what you see there. So when you shifted him by 90 degrees, you've shifted him by enough that the 0 that's over here is now sitting right here, which is what you got. And this keeps going. So, here we've gone by 120 degrees, and so now we're taking a whole lot of sine and a negative amount of cosine in order to get it to start negative. And, et cetera, et cetera. Here's moving it by 180 degrees. So if you shift it by 180 degrees, shift a cosine wave by 180 degrees, what you have is negative cosine, right? The next peak down, the next negative peak now is sitting at 0. Here it is. And it's the same as cosine flipped and multiplied by 1.6, and so the weights are negative 1.6 on cosine, no sine. I don't think this pill keeps going, does it? No, good. Okay, so I've built up a description of the way cosines work when they're scaled and shifted. Now I'm going to ask, what happens if we put them through one of these linear shift-invariant systems? I'm going to start by putting in the standard cosine wave through, and then I'm going to extend to every cosine wave. And what we're going to find out is that it's going to have a trait that's going to be so simple that it's going to provide us with a completely different way to talk about linear shift-invariant systems. The first way, which we started with the first 45 minutes of class, was the same as what we do for any linear system, which is you calculate those impulse responses. Shift-invariant said those impulse responses are all the same as one another shifted, so you only need to measure one of them. And so you measure that vector of responses to a single kick, and you're done summarizing the way the system works, and you can predict its output to anything. Now what we're going to say is its output to cosines is particularly simple and can be summarized by, it turns out, two numbers. And so that if I measure its output to cosines of various frequencies, I've also summarized the system, and that summary is incredibly useful, and that it is intimately tied to the summary I gave you a moment ago, which was the impulse response. And so that's the big structure that we're building up piece by piece. So the next piece of that structure is to say, let's put a cosine wave into a linear system. Now what happens with a cosine into a linear system? Well, you've seen this formula before. It's convolution. Now there were two convolution formulas. There was one where R runs backwards and the input runs forwards. And there was an equivalent one where the input runs backwards and the impulse response runs forwards. So this is the second one of those. Okay, so everybody recognize the formula. N is the length of your vector, and as we run forward through the impulse response, we run backwards through the input signal. We're going to put this into our system. R is the impulse response that we talked about at the beginning of class. Kick it at time 0 and see what happens. And the output at all times is the output perspective of the matrix multiply. The input at all times is going to be convolution, which is this formula. Now, before I get to the next step, let's look at a piece of this formula. A piece of this formula is cosine omega times little n minus little m. That's a piece of this formula, which equals cosine omega n minus omega m. Look familiar? We have a trig identity for this. It's cosine A minus B, right? So we're going to use that trig identity. So this is going to be cosine omega n cosine omega m plus cosine, that's horrible, unreadable, plus sine omega n sine omega m. We're going to use that. And I'm putting it on the side because the slide skips a step. And so I want to make sure you understand what the step is that it skipped. Every term in here is r times cosine cosine plus sine sine. And we're doing a sum. So we're going to get this guy, one term is going to be all of this. Okay, I'm going to draw a line because I'm going to do some more stuff. One term is this times r of m. That's one term. And we're summing over m. Okay? That's just the first step, is I'm taking this thing and subbing in for that guy. Now what we're going to do is pull out all the terms that have cosine omega n and put them in this place, and all the terms that have sine omega n and put them over there. We've got a whole things that are being added together. There's two terms times m. We have two m terms. So I'm going to resort them and put the cosines in one place and the sines in another place. So I'm going to take the sum of these plus the sum of these. Okay? And that's what you have here. Okay? So I just wanted to fill in a couple of intermediate steps because there's a bunch of steps on the slide skipping between the first one and the second one. Okay, so I'm putting in a cosine wave, and now I've got this sum that, in terms of your vector, we're saying what's the output at time n? It's got something to do with a cosine wave. Here's a cosine wave, the standard wave we've been talking about all this time. Here, this term is a sine wave. And then all of this part doesn't involve n. There's no n in there, which means all this stuff is a constant that has to do with your impulse response, R, and has to do with what frequency are we talking about. So I'm going to take, so what we've seen is we've now got a weighted sum of a cosine and a sine, which means the output is going to be the same damn frequency. Some stuff might happen to it, but we're going to get another cosine wave, or its wave, coming out with the same frequency. How do I know that? Cosine omega n doesn't depend on n. It's just a thing that I can pull out. Then I've got this sum, which is a number. And this sum, by the way, looks a hell of a lot like a dot product, right? It's a dot product of my impulse response with a cosine of the frequency that we're talking about. Summed over m, so it's a dot product with our standard cosine wave. This is a dot product with our standard sine wave. So I'm going to get these two weights by doing this dot product. I'm going to give those weights names. I'm going to call it the cosine part at frequency omega of my impulse response R, and the sine part of frequency omega of my impulse response. So R is sitting in here. I'm going to say, R, let's dot product you with a cosine wave and get a number. Later on in the semester we'll talk about correlation. I'm going to correlate. I'm going to say how similar is my impulse response to a cosine wave. Now, why am I using the word similarity? So these are vectors and they're getting dot products. Imagine that I normalize this, made it length 1. I haven't yet, but let's say that I did. It's a vector in my 32-dimensional space. R is another vector in my 2-dimensional space. If R is pointed in the same direction as my cosine, I'm going to get a big dot product, because all I'm doing is projecting onto the cosine, especially if I made it unilength. I'm just projecting. So if it's pointing in the same direction, I get a big number. If it's perpendicular to it, I get nothing. So I'm asking, basically, is my impulse response got a lot of this cosine in it? And if I do, this number will be big. My sine's pointing in another direction. Later on, I don't think I do it today, I think I do it next time, but I forget. I'm pretty sure I do it next time. Later on, I'll point out to you that this cosine omega m and this sine omega n as vectors are not only different vectors, they're actually perpendicular. We'll get to that later. But they're helping us define a space, which means it's not pointing this direction, it might well be pointing in this direction. So we're going to ask how much. It might be pointing somewhere else entirely. It may not have any of this particular frequency in it. We don't know. But we find it by basically doing these two dot products. And so what I've just said is the output to a cosine is a weighted sum of a cosine and sine of exactly the same frequency, otherwise known as this picture. A weighted sum of a cosine and sine, I just said in the last slide, is a general cosine of that frequency. It may have a different amplitude. These weights could be big numbers, they could be small numbers. Don't know what they are yet, haven't talked about them. But they're just numbers, two numbers. They are aspects of your impulse response, R, measured by dot products with, some vector. So you're just getting two numbers out. Those two numbers could be big, in which case this guy is a cosine wave with big amplitude. Those numbers could be small. Those numbers could enforce, when you do them in polar coordinates, a phase delay. So it could come out as a sine, even though we put it in a cosine. It could come out as a halfway between a cosine and sine. It could be phase shifted by more than 90 degrees, or by pi over 2. Okay? But whatever it's going to be, it's a weighted sum of cosine and sine, and we've already characterized what are all the weighted sums of cosine and sine. They are cosines of exactly the same frequency, possibly amplified, possibly phase shifted. So I've already told you that if you give me a cosine and a sine and allow me any possible weighted combinations, I stay in the plane. Now what I've told you is if you put that cosine, this particular one, and put it in the system, it stays in the plane. And what I'm about to tell you is you take any point in that plane and put it through a linear system, you stay in the plane. If you put in frequency omega into a linear shift-invariant system, what you get out is going to be a cosine wave of frequency omega. That's the implication of this math. And I will continue to develop that as we go, but we're basically there. We've we've just said that I'm going to do these dot products of my impulse response with a cosine and my impulse response with a sine. I get these numbers. Like x and y multiplied by cosine and sine, they can also go to polar. And if they go to polar, so x is a times cosine of phi, and y is a times sine of phi, this is just the usual polar transform, we now have a and phi, which means we know what cosine we're getting at. We're getting a cosine with this amplitude, and we're getting a cosine with this phase delay. It's the same math being used, but now, instead of going from polar to rectangular, I'm going from rectangular to polar. Okay? But it's the same exact math. I have used a notation here that's meant to preserve what these numbers depend on. A isn't any old amplitude. It's an amplitude that is a trait of your impulse response at this particular frequency. Right? Here's your impulse response. Here it is being correlated with a sine and a cosine wave at that frequency. So A is going to depend on what system we're talking about, that's R, and it's going to depend on what frequency we're currently talking about, which is omega. Similarly, phi, phase delay, is going to depend on what system are we talking about, R, and at what frequency do we have this phase delay. Other frequencies could have other amplitudes and could have other phase delays, but for the frequency that we're working with, omega, we can do the math and get, oh, that frequency gets amplified by this much and gets phase delayed by this much. Now the math that I have, oh, am I jumping ahead? No, oh yes, I'm jumping slightly ahead. And so what we've just said, oh, and then, this is a weighted sum of cosine and sine, so the same trig identity we were using a minute ago, we could use backwards, right? Cosine A minus B is cosine cosine plus sine sine, or cosine cosine plus sine sine equals cosine A minus B. Same trig identity, just we're using it in the other order. Okay? So what we've now derived is if we put a cosine, standard cosine into the system, starts high, goes low, high, low, high, low, high. Now I guess I've got k equals 3 as the frequency, right? Because I see 3 cycles there. But if I put k equals 3 in, I get k equals 3 out, amplified by whatever A turns out to be, and phase delayed by whatever phi turns out to be for that frequency, for that system. Okay? So, linear shift invariant, thought about the first way, is you kick it and you measure what comes out. And if you kick it at any other time, you get the same thing out, shifted. And if you kick it harder, you just get the same thing out scale. That was our previous way of talking about the system. Now we have a new way of talking about the system, which is instead of kicking it with an impulse, you give it a sine wave. And no matter what frequency you give it, no matter what omega is, the way we're going to think about it because we're doing discrete, is no matter what k is, as long as it's an integer, no matter what k is, what you get out is the same exact frequency, possibly shifted in time, if you think of the x-axis of time, and possibly amplified. Which means that to say what cosine does, we only need to know two numbers, a and phi. Right? Our summary of what it does to cosine, we don't get some arbitrary output that's jumping all over the place. We get a cosine wave that maybe is scaled, so I need to know the scale factor. I need to know a. And maybe is delayed, so I need to know how much it's delayed by. Okay? And so I summarize the behavior of the system at that frequency with those two numbers, a and phi. Now, here's where it gets more general. Suppose I didn't put in just cosine omega n. Suppose I put in a cosine omega n minus phi. Suppose the input, and I'm saying this is the input by putting little x subscripts here. Suppose the input is now delayed by some amount and amplified by some amount. So I didn't just put in the standard cosine, I put in another sine wave of same frequency, but possibly an amplitude different from one, and possibly not in cosine phase. Now I could go through all the ugly trig that I just did, made uglier because now we've got a phi and an a to carry around, and do all the math. But we don't have to. Why not? It says it right there. This is a linear shift-invariant system. I know what it does with cosine omega n. I've just multiplied by a, so the output is going to get multiplied by a from from what it would have been. What it would have been is AR cosine omega n. So I scaled the input, so I'm going to scale the output. I also delayed the input by phi x, which means I'll get the output I would have gotten delayed by phi x. The output would have been omega n minus phi r. That's what I did in the previous slide. And so now all I'm doing is delaying it by the amount I delayed the input. So what I've now shown you, what I said about a few minutes ago, we have an input that lives in the plane. It is a cosine of frequency omega, or if you do the integer frequencies, frequency k. We already know that that cosine wave lives in a plane defined by cosine omega n, sine omega n, which are not, my standard axes. It's a new set of pair of axes. I know that this new input is living in the plane, but what I've proven is that when it goes through your system, you're going to get another cosine wave of exactly the same frequency, possibly phase delayed by some amount, possibly amplified by some amount, which means it's going to stay in the plane. It's going to go somewhere else in the plane. It's still a linear combination of cosine and sine, because it has an amplitude, ARX, it has a delay, phi x plus phi r, and we know how to treat that and where that is in the plane. So what we said is any cosine of any amplitude, any phase of that frequency goes through your system, and what comes out is possibly amplified, possibly phase shifted, the same exact frequency. At the end of the linear systems theory section, otherwise known as the previous class, one of the last things Arrow did, actually I think it was the very last thing he talked about. He talked about symmetric matrices and some nice properties of them, and one of them was if you do PCA, if you put in this vector, and it's a vector that's one of the principal components, it's one of the columns of V, and you put it through the symmetric matrix, all that happens is it gets amplified, but it doesn't get rotated at all. It doesn't point anywhere else, it stays. We call that an eigenvector, and an eigenvalue is how much it got amplified by. We have a kind of a generalization going on here. If a system is linear and shift invariant, it has these pairs of vectors where if you live in that pair of vectors and what it spans, you stay there. So we don't have eigenvectors. I mean, it's a matrix multiplying, it also has eigenvectors, but we're not talking about that now. But we have these eigenplanes, meaning if you are in that plane and you go through this system, you're going to stay in the plane. Now, if I change omega, that'll be a different plane. Turns out it'll be orthogonal to the plane we started with, but we'll be in a different plane because now k equals 4 instead of k equals 3 from the example that's on the board. So if k equals 4, and I put in a generalized cosine with k equals 4, it's got 4 cycles per length of your vector, and I put that in, what I'm going to get out is a sine wave with k equals 4. It might be phase delayed, it might be amplified, but it'll be a vector in that new plane that we put the input from. So in other words, if you think of all possible inputs as being all the k's we have, that's something I'm going to develop next time, not today. So if we think of representing our signal as a bunch of sine waves of different frequencies, then what I'm saying is the linear shift-invariant system treats each of those frequencies independently. No cross products, no interactions, nothing. Frequency k, frequency 1, becomes a frequency 1 in the output. Frequency 2 in the input becomes a shifted, amplified frequency 2 in the output. Frequency 3 in the input becomes a frequency 3 in the output. So I can represent my input as being frequency 1, 2, 3 up to n minus 1. Frequency 0 up to n minus 1 is what we'll actually do. If that's my input and I describe it that way, then the system is, how much does this guy get amplified and shifted? How much does this guy separately get amplified and shifted? So I separate this guy into a sum. Each of those guys does this. It's got one of these numbers and one of these numbers, and then they get put back together. That idea of a system taking an input x, splitting it up into different components, saying how each of those components will behave when they go through the system, giving those separate outputs, and then adding them back together to get the output. You've seen that diagram before. This used to be impulses what the impulse responses are, get scaled by the input, add them together. We're now going to build up a diagram that looks just like this, except instead of being x at time 1, x at time 2, x at time 3 as the scale factors, now it's going to be how much sine wave does x have at frequency 1? And then do what frequency 1 does. How much sine wave does x have at frequency 2? And then do what frequency 2 gets done, processed by the system, and then take those results and add them back together. It's the same idea of taking your input, picking a representation, having the representation have an incredibly simple description in the system, which in this case, incredibly simple means for every frequency, how much am I amplified and how much am I delayed, and thus predicting what the system does to any input by knowing what it does to a small subset of inputs. In this case, sine waves of different frequencies. And notice that we did not need to measure the system for a cosine and for a sine. We represented everything as how much cosine and how much sine. But we measure it for cosine. We don't have to measure it for sine. Why not? What aspect of the system means that if you measure for cosine, you already know what it's going to do for sine? What's the relationship between a sine and a cosine wave? One is a what of the other? A shift. So shift-invariant buys you that. So, we did this on the slides. We ran the system on cosine only. I never bothered to run it on sine. Because sine is just the same as cosine with this being pi over 2. That's all. So I didn't need to run it on sine because I already know what it's going to do on sine. So used to be, you kick the system and you measure a whole bunch of numbers. The length of your vector, you measure 32 numbers, and you've now summarized your system. Now, you kick it with cosine with frequency 0, and you measure 2 numbers. Frequency 1, measure 2 numbers. There's some subtleties in there that we'll get to next week. You kick it with frequency 3, you get 2 numbers. You collect up all those numbers. By the time you're done, how many numbers do you think you're going to have to measure? How many I have to measure last time? Right. So my system has 32 degrees of freedom, which is the impulse response. So when we talk about it in frequency terms, we'll also need to measure 32 numbers. What those 32 numbers are, that's a topic that we're not going to get to today, as I recall, because that's a horrible place to get stuck in the middle. So unfortunately, oh God, I thought we were there. Maybe we are going to do that today. God, 20 minutes. I was a little worried about that. Okay. Yeah. Well, let's review. Oh no, we're going to get back to this topic a little bit later also. But just let's point out when we put in this general cosine wave. This is the formula I had before, but let's see what the formula does. It means here's the amplitude I put in. It gets amplified further by what the system does at that frequency. Okay? So the amplitude of the input times the amount the system amplifies at that frequency, those two get multiplied. Okay? Phase shifts, on the other hand, get added. We were phase shifting by x in the input, and we were phase shifted further because the system delayed it by phi r. So phase shifts are shifts, and so if you do 2 shifts, the shifts add. Stretches multiply. So thought about it in the polar coordinates way, these guys multiply, these guys add. We'll talk about it in the Cartesian way, but not until next time. Okay. So I guess we are going to be at that point now. Oh my God. I wasn't planning on getting to this today, but I'm not going to stop 15 minutes early, so I'm going to start with this. Oh my. All right. So I would like to say, okay, if different frequencies are handled differently, I'd like to represent my input as sine waves. Because we now, yeah.
Could you possibly give an example, like maybe a worked out example to show and summarize what we just went through?
That's an interesting concept, but doing that without pretty slides in math, I'm not sure what to do. But let's talk about that. Let's imagine that we have a system with an, oh, you know what? I didn't even, there were some examples I was supposed to do earlier that I didn't do. I skipped past them. first of all, let's go to the earlier characterization, the impulse response. Okay? So let's think up some impulse responses that do interesting things. So suppose my one we've had before, so this is going to be the impulse response, R of, okay? And so here's an impulse response, 1, all zeros. We've done that one before. We build our matrix. The matrix is built by shifting. So the impulse response is put here, 1 and a bunch of zeros, and then we shift it, 1, 1, 1. Okay? So what does that system do to the input? The output is related to the input how? It's an easy one, kids. Really easy one. What matrix did I just write down? The identity. This just copies the input to the output. Okay? The impulse is, whatever the input is now, gets copied to the output now, and that's all that happens. Okay, that's kind of boring. Let's make the system a little more interesting. Let's add a couple more ones. In fact, let's make them 1/3 and have 3 of them. Okay? So now I got 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, etc. Okay? So if I kick it, I get something that lasts for 3 time steps. But let's think later on where, we're not dealing with edge effects. Okay, so let's think later on. So for example, at time step 3, so now we're going to look at rows because that's the output perspective. The output at time, let's count from time 0, 1, and 2. So the output at time 2 is 1/3 the input at time 2 plus 1/3 the input at time 1 plus 1/3 the input at time 0. What is that in English? It's an average of the last 3 time steps. The output at time 4 is an average of the input at times 4, 3, and 2. The output at time 15 is the output at time 15 is an average of the input at times 15, 14, and 13. It's usually called a running average because it's an average that's running over the input, and each time it's an average of the recent past. Okay? That's a good example. Let's try another example. Well, let's suppose that the impulse response is 1 minus 1. Okay? So here's our matrix. 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, dot, dot, dot. Let's take any given row. This is the 4th row. The output at time 4 is the input at time 4 minus the input at time 3. So it's computing a difference. It's computing the discrete time best you could possibly do, which isn't very good, of a derivative. It's saying, what's the slope? How much are things changing right now? Okay, so these are all useful things. I think there was a slide with these examples, or there's something written somewhere that says other examples I should do, so I'm going to take a peek and figure out which examples I had meant to do it and blew right past. Examples, so it calls delay, average, difference. Okay, I didn't do delay. All right, so here's delay. This is 0, this is 0, this is 1, and everything else is 0. So now the matrix is 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. And so in that same 4th time step, my output at time 4 is what my input was at time 2. So that's like one of the guitar boxes that you plug your guitar into that adds a time delay that you can add to your own signal to give you echoes or whatever. Okay, so this is all in the time domain. This is all from the very first half hour of today. But now we want to go into the frequency domain. So let's go into the frequency domain for some of the simplest ones. So let's go to the simplest one of all, which was the identity. Okay, so going right back to the first example, was an impulse response, which is a 1 at time 0, and then all zeros, where the matrix is the identity. Okay? But now we're going to, are, is there a pretty version? Yeah, there we go. Okay. So now I have to compute, oh no, that's not what I want. I wanted these guys circled. I don't know if I've got on a slide looking nice. I mean, it's good enough. Did I? Yeah, there we go. That's what I meant. Okay, so now I'm going to compute these numbers, which are, take my R, which is sitting right there, 1, 0, 0, 0, 0, and I'm going to correlate with a cosine and a sine. Now, I don't care which frequency you pick, cosine omega n is always going to look like this. No matter what omega is, it's always going to start at 1. And sine omega n is always going to look like this. So no matter what omega is, I'm going to do a dot product of this with that. Just what's written over there. And this is 0 everywhere except for the first place. Which means when I dot it with cosine, I'll get 1. Independent of frequency. And when I dot it with sine, I'll get 0. Independent of frequency. So those two numbers, the cosine part is always 1. Doesn't depend on omega. The sine part is always 0. If the cosine part is 1 and the sine part is 0, in that space of cosine R of omega and sine R of omega, I'm sitting right here at 1. 1. Right? I got a cosine part and no sine part. Which means that if I put in a cosine wave of any frequency whatsoever into this system, I am going to give it an amplification of 1, meaning I'm not going to amplify it, and I'm going to give it a phase shift, the angle, of 0. Otherwise known as, when I put in cosine waves, they don't change. I already told you this is the identity, so now it's in the frequency domain. It's the identity. It doesn't mess with your signal. Okay? Let's talk about, okay, without the next math, doing an example more complex than this is interesting. Let me think about what's a good example to do that's, okay, yeah, let's do it. Here's an obvious next example. Suppose that my impulse response, we've been calling the length of the vector capital N. Suppose, here's my vector. And, just for grins, I'm going to call this 1 over N. Okay? So, this thing is taking the input and just measuring its average, or whatever. Kind of a funny impulse response. It's staying constant for the entire length of the vector. Now you may worry about boundary effects, but we're going to act like things circulate, which means that even when you shift it, you get it right back. So it's just, no matter where you are, you're getting the same answer. Okay? So now let's think about what you get when you figure out these CRs and CSs. So for any omega that is non-zero, for anything that wiggles, I'm going to take this and dot it with that to get these CRs and these CSs. And the dot product of this with that is going to be what? Don't need to do the math, just look intuitively at the picture.
0.
It's going to be 0. Why?
Because it cancels out.
Because it cancels out. There's an up, and then there's a down, and there's a down, there's an up, there's an up, and there's down, there's down, there's up. And it's going to perfectly cancel out. Why? Because I'm only allowing k to be an integer. So there's always an integral number of cycles. So it will always perfectly cancel out for any frequency except
0.
frequency 0. We've never talked about frequency 0, but k is allowed to be 0. Now frequency 0, as we'll see at the beginning of next time, is annoying and special because what's a sine wave at frequency 0? Sine 2 pi frequency 0 over capital N times time m. What's that wave?
Zero.
It's all zeros. You can't do anything with it, okay? So we're never going to actually use that one. What's the cosine equivalent of that?
1.
It's all ones. It's our vector, okay? So there's only one CS omega, CR of omega that's not zero, and that's CR for frequency 0. And that's a dot product of all ones, 1, 1, 1, 1, 1, 1, 1, with this guy, and its value is 1. Okay? So when you give this thing an input, if it has any frequency whatsoever, it's thrown away. It's gone. However, if it has some input that's not wiggling, meaning if your input signal has an average that's non-zero, that average will be output, always, at all times. Okay? So it's taking kind of the constant function that you've given it, and it's preserving that, and it's taking any modulation of that function and throwing it away. Another way to think about this thing, it's being convolved with your input, which is to say you're averaging lots of your input, which is you're blurring your input until there's no form left, and all there is brightness. So if you think of the input as an image, fine, we've only got one dimension, so image is kind of funny, but it's a one-dimensional image. If it has any pattern in it, any bright spots and dark spots, goes through our system, they're gone, because we've taken an average of everything and just output the average. So we've blurred it to smithereens. But if I take the whole image and make it brighter, that brightness will remain, because I'm retaining the average. Okay? So I've done some extremes about all frequencies get through or no frequencies get through. This idea of which frequencies get through, this filtering of my input signal by which frequencies get through and which don't. We need a little bit more math and a little more thinking about it until I'm ready to talk about that. But that's what you mean by the frequency description. You're saying my input has some fast wiggles, some slow wiggles, some very slow wiggles, and some no wiggling at all, some just constant input. And I say, which of those get through? And this one, this impulse response right here, deletes all modulations, all frequencies, and only lets frequency 0 get through. This one lets all frequencies get through. When I go in between, this was my averager as an impulse response. So a wiggle that's so fast that it goes up, down, dotted with this, will cancel. That's a really high frequency. A frequency that goes really slowly will get through because it'll have a non-zero dot product. And so this one will quash high frequencies, and as the lower they get, the more that'll get through. The more of these I include, the fewer frequencies that get through. Okay? So that's just an example. I'm not actually doing the math, but you can imagine if I have like 8 of these, somebody goes up, down, up, down, up, down, up, down, cancels, dotted with this. Somebody who goes up, down, down, that's half the frequency, cancels. Somebody who goes up, down, cancels. But somebody who goes up for 8 and goes down for the next 8 and up for the next 8 and down for the next 8 doesn't cancel. So what I'm saying is, if you average the input for a long period of time, then you're blurring the hell out of it, and so high frequencies get quashed. Okay? So that's a bit of an example to think about intuitively this math. Which frequencies get through, which don't, or which frequencies dotted with this, correlated with this, give you big numbers, they get through. And if they give you small numbers, they don't. Now if I take this guy and shift him over, that's going to switch between cosines and sines. And, so there's a phase shift involved. That'll show up as phi, which will show up as a different weighting between correlate with cosine versus correlate with sine, which I've been dancing around. So that's a little bit about it, with the intuition of where the math is going. Where we're going with this next, and I'm glad that I didn't try to start it today. The very next step is to build up this intuition of cosine and sine are 2 axes in our 32-dimensional space. If I go to another frequency, those will be 2 more axes. Can I build up a matrix out of sine waves that does exactly what we want? In other words, that is a rotation matrix. Can I build up things that look like cosines, but I'll, by fiat at some point, make them one or not? Maybe I won't bother. We'll talk about that. But if I have frequency 0, that's cosine only, sine frequency 0. frequency 1, frequency 2, frequency 3, frequency 4, a bunch of frequencies, and I call those the columns of a matrix that re-represent the signal, and re-represent it because of math we already know. Because if it's a cosine matrix, then you take our signal, you multiply it, you're just rotating it. You're re-representing it in a new coordinate frame, but you're not losing any information. That's where we're headed. Having done that, we can take any signal, rotate it into sines and cosines, use this math to say systems treat that really simply, and then rotate back. That's kind of the outline of